Hello everyone, my name is Yangyang Chang. I'm today's presenter, and co-author is Gerald Sobelman. We are from Department of Electrical and Computer Engineering at University of Minnesota. My title is the skilled quantization for the vision transformer. Yeah, and the next page. So this is my outlines. We have several topics today. The first things I want to talk about, go overviews of the lightweight deep learning neural network designs, and then go through the direction of the research to the quantumization, and talk about the vision transformer of our paper, for example, and then I will talk about the contributions of our paper. After that, and I want to talk about our quantumization process for the vision transformer, including the basic quantization operators, how we can handle the overflow, and the quantization process for the vision transformer. In the result part, I will talk about the memory reduction and our simulation environment and our mean square error results. After result part, I will talk about the conclusion and the future work. Following that will be the reference. Okay, first I want to talk about the lightweight deep learning neural network designs. Summarize the 7 factors over here. We want to design the lightweight deep learning neural network because right now, the huge parameters of the deep neural network is hard to implement on the hardware. So we have 7 directions over here. The first is like, we can directly design the lightweight operator. For example, in the mobile net, it's a type of lightweight convolutional neural network. It's basically you utilize the depth-wise separable convolution. So it can save the huge computations than the standard convolutional operators. And for example, for the non-linear activation function, is called rectified linear units, and with maximum 6. And this new design can increase the classification accuracy, and also, just with the same simple rectified linear units operation design. And we can also go for the data compression, and there are 2 categories, lossy method or lossless method. If we can reduce the capacity of our inputs, we definitely can scale down our following deep neural network. And the third factor is the target-based architecture that we redesign. Based on the target, we can redesign our architecture. For example, I give here the example of the natural language processing. So the architecture is involved from the long short-term memory to the transformer with attention. So long short-term memory has a huge parameters, but right now the transformer with attention just has the decoder and the encoder, and also can do the parallel computation. And the fourth factor, we can also go for architecture optimization. It's also called the neural network search. And so it's a kind of like you have like the baseline of the architecture, and then you have to use the optimization function to search which layer you want and what's the computation you want. So this NS will give you the favorable trade-off between the computation and the classification accuracy. And the fifth factor is called purging method. And this is called weight purging or filter purging. Weight purging is like you want to remove weight or remove some like redundant kernel or called filter. And the sixth factor is called hybrid architecture. And here I directly make the citation of reference 11, and it's called the COCO. This COCO architecture is the first rank on the ImageNet 1K so far. So because it has a dual transformers. One transformer is for the input test, one transformer for the image. It also has less parameters than the previous architecture. The final thing is we can also do the quantization. This is most hardware friendly. And we also have 2 categories, deterministic and stochastic. Deterministic is like we want to map the quantization value to the real value. Stochastic, we want to map the quantum value to the distribution of the real value. Okay, so let's move on to the quantization. The goal of quantization, we want to use a lower bit width than the full floating point precision. And the merits from this quantization, I mean, advantages, first, we can accelerate the training and the inference process because we reduce the learnable variable gradients operators to a small number of bits. And also we can achieve very good hardware design. It's very friendly. For example, if we have integer bits, we can directly use or AND gate. Pretty much we can utilize all the shift parameter and the gate level design. Directly design a chip based on this, based on the quantized machine learning model, or you can implement the quantized machine learning model on the FPGA or some hardware with a limited memory or computation. So it has three categories: deterministic approximation. First is the deterministic approximation. So we need to estimate the real values. And second is deterministic optimization. And this method optimizes the bit length or the selection of the binary bit for the real values. And for third category is the stochastic quantization. Like I said in the previous slide, and the quantization values are sampled independent from the assumed distribution, like the multinomial distribution. So now we can find some problem. It's like, first, if we want to do the approximation in the backpropagation and the forward path, normally we'll face the unbalanced approximation problem. Because we have to use a different quantization method. Therefore, the better way is to choose the post-training model. So we train the model in the floating point number, but when we implement for the real in our real world, we want to use the post-training, and we quantize the post-training model. And the second problem is like, if we want to use the assumption from the assumption distribution, when we in our real world, when we have the noise input or our input are different, this distribution will change. So the better we actually go to the deterministic quantization. But when we talk about use the deterministic optimization problem, if we use this method, we have to has also enough computations because we need to search what we want. So what we want for each bit, we need to know which parameters have which specific bits, or which should be 1 or 0 for the binary bit. So we need to have enough hardware to do the optimization process. So if you don't want to do that, so the better way to actually go the deterministic approximation. And when we set this method, we also need to think about how we can view some parameters that cannot be quantized. So we have to redesign it, or when we pass these operators, we have to convert back to the multi-bits real value. Okay, so here we in our papers focus on the vision transformer, and so here I just gave an example of the cold scale vision transformer, and I think that published the last year is a pretty new one. So here I directly present the two unique blocks from this paper: the convolutional attention and the scale and the serial block. For convolutional attention, because we need to do the quantization, we can directly find what specific operator we need to quantize. And this is the QKV, the just attention matrix. We will not change it. But for softmax, we need to quantize it. Depth-wise convolution need to be quantized. And depth-wise convolution again. And also we have concatenation, reshape. This is just, changes the shape of the tensor. And also we need to care about here is the metric product, Hammond product, and element-wise summation. For the serial block and this convolutional attention, is already from the left side figure. And what we need to care about is the feed-forward operator. Okay, so now let's talk about the contributions of our paper. So we propose the full integer quantization of the vision transformer networks without requiring any intermediate floating point computation. In other words, our method can directly make a chip or directly implement on the hardware with limitation of the computation and the memory. And then so we face post-trained models, so there are no worries about the training process. In our paper, we covers all the methods from the basic operators to the large models. You can see including all the addition, subtraction, multiplication, and to the activation function, convolutional layers, and so on. And in our models, like I said, we are very hardware friendly. Because our operator design due to use a simple multiplexer and shift operators. And because we covers all the basic operators, all this deep learning neural network use the same operators, our quantization method also can be applied to the different DNA model. And finally, because we use simple multiplexer shift operator, therefore, our method can be applied in various hardware, software implementation, including process, memory architecture, and FPGAs. Okay, now let's talk about more complicated thing. So it's pretty much mathematics because deep learning network is based on the math. So we first let's talk about the basic quantization operators. So we call them as the ScaleMultiplication, ScaleAddition, the ScaleSubtraction. So first we need to initialize it. Once we have floating point number, we need to convert it to the multibase, our quantimes the value. So we'll pretty much follow this first equation. And the F value is close to or larger than the maximum R. So what's the maximum R is the maximum value of the one hidden dimension. So it's pretty much like, for example, we have one hidden dimension had 1,000 data, we need to find the maximum value. Use this maximum value, we need to find some F value larger than this or closer to this maximum value to find the scale value as is an integer. So once we have this as integer, for all the values in this one hidden dimension, their scale value will be the same. And then so because we need to do the quantization and we want to do the 4 integer quantization, and the p-value is set to 8 bits. And the maximum memory size of the scale we set to 5. So after we find this S value and all the parameter for this one hidden dimension are rounded after multiplication of the 2 to S. So we found this times to the previous decimal value and then rounded to the integer. So the pretty much like approximation method. But the difference is like we did not directly estimate the integer value. We also use the scale value with the integer value, so we can get the more accurate result. And so how we can do the multiplication? So for previously 2 floating point number is equal to the 1 integer value over the scale 2 to scale times another integer value over the 2 to S2. So we times the 2 integer, and as you can see, what we only can do is we directly do multiplication between the 2 integers and over the 2 scales, just do the addition and the summation. So it's pretty straightforward. So maybe you have questions about why we focus on the power of 2. Because in the hardware design, if we can do the 2, over 2 or multiply 2, we can directly do the shift operator. So just shift the bits. It's a very fast operator than the multiplication, addition of that design. So for the scale addition and for the addition part, summation part, because we have the scale in here. So for when we do the summation of the 2 integer, and we have 2 times another scales, so S2 minus S1, so to get the final integer value. And the scale will be updated to the maximum value of these 2 integers. Use the same thing, we can also do the scale subtraction. And now we move to the more complicated part to talk about the scale division. So why we need to redo the division? Because the division is very hard to achieve in the hardware design. Normally you have to have several iterations to get the precision, high precision. So in the quantization, we have to redesign the scale division. So here is the function. So as you can see, if we have the 2 integer 1, integer 2, and we want to find the quotient. And once we find the first quotient, and we will remember this value. And then we will this REM means remainder. So first integer, second integer, to the quotient, we will have the remainder. Remainder times another 2 to C1. In other words, to make the larger than the integer number 2, and we will do the quotient, we will get the quotient again. But this quotient will have the new scale value called C1. And then so we will use the same procedure to get a new quotient. And if we have enough quotient, and we will get the very great, division value. So I think it's a little bit hard to present. So I gave the example over here. For example, we have 11 with scale 3 and 20 with scale 4, and our division loop is 3. It means we only will do 3 quotients here. So 11, so the real output value should be 1.1. In other words, 11 over 2 to 3 and over 20 over 2 to 4 should be 1.1. Okay, this equation, step 0, we only want to handle 11, 20 with and scale 3 first, and handle the scale 4, second. At the step number 1, first because 11 cannot over 20, we need to times another 2, make it to 22. And because we times 2, so new scale will be add 1. So it will be 3 plus 1, we can get 4. So because the 22 larger than 20, so we can get the quotient is 1, and remember, remainder is 2 with the new scale 4. So, and then, so the new remainder 2 is less than 20. So 2 is times another 2 to 4, we can get 32 is larger than 20. Now we can get the new quotient is 1, remainder 12. So we do 3 times. Finally, the summation will be like 1 with scale 4 and add the 1 with scale 8. The 1 is from the first quotient. You can see 1 from step 2, step 4, step 6, we have the 3 quotients. And the 1 with the scale 9, once we add all of them, we can get 34 with scale 9. So this 34 scale 9, and then we can do the division, because previously we also have scale 4 from the 20. So we have to do the 9 minus the scale 4, we can get 34 over 225. And the final division number, we can get 1.0625. So it's very close to the 1.1. But this example only do 3 division loop, only 3. But in the program, we will do 5. Okay, so when we do the operation, in the deep learning, there are many data, and definitely will have some overflow problem. So overflow problem is also very straightforward, because we want to save the computations. So if we found this integer is overflow, and we will save this overflow to the temporary memory, and then we will only keep the PMSBs and save to the new save it to the new output of the integer. But once we have this overflowed integer output, we definitely also need to deal with the scale as well. So, and we need the new scale after the scale operation between the integer 1 and 2, and we need to manage the number of bits overflowed. So from the algorithm, a little bit hard to understand. So let's go for the example. For example, our P is 2. In other words, the maximum length of all parameters is the length of the bits. For all the parameters is 2. And if our output integer is 6 and the scale is 1, and the real value we can find is 6 over 2 is 3. And we know the 6 is a 110 in the binary format, and we only want to keep the 2 MSBs. We can get 3 because we only want to keep 1 and 1. And the new scale value, and we need to manage the number of bits overflow. So 1 minus 1, we can get 0. So the final real value will be the 3 over 1 equal to 3. So even we handle overflow value, but we can still get the same result. Okay, so now let's move from the basic quantization to the real quantization layer. Here in this slide, I talk about the 2-dimensional standard or depth-wise convolutional operator. Here in this presentation, I directly give some basic functions. If you want to know more details, you can look at our paper. So for the convolutional operators include element-wise multiplication and the partial summation. So we can directly deal with the scale multiplication, scale summation, and the scale subtraction. I talk about it in the previous slide. For element-wise multiplication, it's for each width times each input. And you can see you directly times two integers, and two scales you can directly do the addition. And for partial summation, it's like you need to, so we have to add all the element-wise multiplication output together. So we add them up, and we need to find for this scalar, we need to find what's the maximum scales for that. So we find the maximum scale from all the scales from the outputs of the element-wise multiplication and add them up. So pretty much you utilize the basic operator we talked about before. Okay, so then, I want to talk about the quantization process for layer normalization. This is a layer normalization calculation equation. As you can see over here, it's like what we handle is the inverse square root. It's very hard to achieve in the hardware design. So how should we do? I directly use the Newton method. So first I create the equation is like a y equal to the inverse square root of the x. So we can get the function fy is a y over y square minus x is equal to 0. And then we want to find what's the y value for this function. As you can see, we use Newton's method. Y is a j plus 1 and equal to yj and minus this whole equation over here. So after you deal with this equation, we can find the final equation over here. And then but this is only for mathematics equation based on the floating point number. And we need to convert to our quantization equation. And then so we convert the final this equation, go to the yj plus 1 over 2 to sy0 over here. So what's the y0 here? It's the initial Newton's method, because we need to give the initial point to find the final value of the inverse square root of the x. So as you can see, I add many the scale over here because we need to finally deal with both scales and the integer value. Okay, so here I give you our one test about the one square root of the 15.25. If we use Newton's method and also use the floating point 64, our initial value is 0.01565. But for quantum approach, we have the integer 1, and the scale value is 6. And then so we do the same thing. You can see here the input is 15.25, and our input is 122, and the scale is 3. If you do the math, it will be the same value. As you can see, we only do the 8 iterations. The final real value, 1 over square root of 15.25. The final value should be 0.2561. But if we do the floating point is 64, the error between them is larger than our quantization method. So in other words, our method also can get a very close value and also better than the floating point 64 operators. Okay, so after that, let's talk about the linear transformer and the convolutional attention from this Subtraction transformer. So you can see all these operators, linear transformer and the depth-wise convolutional, element-wise summation, element-wise product, we can easily implement as scale multiplication, scale summation, and all of this without any scale division. However, for the softmax is a problem, right? Softmax has the exponential part. So in our paper, we use the truncate Maclaurin's series. In here, so we directly use the first 3 terms. So exponential part is a chain to 1 plus xi plus xi squared over 2. And then we add in scale over here. You can see this is a square and the xi and times another 2 to sxi is this one scale the skew of the x, and one will be the 2 s sxi, because the square root, the x square over here, so we need to add a 2 over here. So pretty much we can achieve the softmax with the Multilayer series. And then, so let's talk about the final operator. It's called multi-layer perception. It's a feed-forward network, and also in the vision transformer as well. So for the rectified linear unit activation function, it's very straightforward. Just to finish the maximum and also the compression between the two parameters. But in the vision transformer and also the new COCO, that architecture use Gaussian linear activation function. And for here, as you can see, first we need to do the mathematical approximation, and we get this hyperbolic tangent function. And then we also change to the exponential part, and then we do some mathematical functions. Then, so we also do estimations of the exponential functions by the Multilayer series with the 4 terms. We can get x minus x cubed over 3. And once we have that, when we can get the final 2 function, 0.5x times 1 times a times a cubed. This a is equal to this value. So 18 over 229 is almost equal to 0.035677. So we also do the quantization for this, Gaussian linear unit activation function. Okay, so once we have all of this, we definitely need to show how much memory reduction we make. The first is like our quantization bit is 8, and the memory size for stored skew is 5 bits. So in other words, the skew value is from -16 to 15. It's a very large value, because the 2 to 15 is already over many. We can achieve the decimal position to the 15 bits. So for the, and also for, we have the reusable temporary temporary memory to store overflow data. So we will reusable the temporary memory. We won't create many temporary memory for the overflow data. And finally, if we do the calculation for the total memory reduction factor, compare with the 14.64, we can get 64 over 8 plus 5, because we have 8 bits here, 5 bits for that store the skew. We can get 4.923 for the memory reduction. And then, so for all this, for talk about the operation, for skew multiplication, we require additional skew, addition. And for skew division, and we require the actual addition and subtraction operations. And our 2x, skew addition or multiplication, and we can directly utilize the hardware shift operator. And so, and all of this can be done with the simple multiplexer and the shift operators. So it's a very hardware friendly. So in our simulation environment, and we focus on the mean square error. We will compare with the results from floating point number and our quantized number. Okay, so as you can see, quantum number, we call it output Q, and the real value, we call it output P. And the O means the size of output hidden dimension, and the C means the input size, like if we have 32 times 32 image, it will be, C will be 32. So pretty much like we do the mean square error, and this item is for the quantization, and this item will be real value. So we will compare each values and to calculate the mean square error. And for layer normalization, as I talk about, our initial Newton's method, the Y0 is 0.015625. And in our quantimes, the integer will be Y0 is 1 and skew will be 6. And we have, in our experiment, 100 images from ImageNet randomly selected, and all these images are modified to the 224 times 224. And every image is tested by 25 times. So this is our result. As you can see, our MSE is pretty much less than the 0.01. And for all this layers in the vision transformer. So this is the conclusion part. It's like we first propose the quantization method, fully integer quantization processor for the vision transformer. And we gave the quantization method for all of the basic operator in the vision transformer and without any intermediate floating point calculation. And for each operator, our total memory reduction can do 4.923. And all our operator can achieve by the simple multiplexer and the shift operator. And also we can achieve very small MSE. So as you can see, we did not test any classification results. So this is a part of future work. And we need to replace all the operators published in the GitHub of this vision transformer. We need to replace them with our quantimed operators to further test the classification accuracy. And then we also want to optimize the number of bits by some optimization method like the evolutionary algorithm to better train our quantization process. And that's it. So any questions?